Hello, my name is Max. I'm creator and one of the maintainers of mutation testing library for PHP called Infection. What we will discuss today? We will discuss a couple of things. The first one will be code coverage. I will show you pros and cons of this metric. I will show you why you shouldn't use it alone for your projects. We will discuss what the mutation testing is and how you can use Infection PHP mutation library in your projects and on continuous integration servers. So what is really code coverage? Before we go deeper, let's get familiar with types of code coverage. There are at least three of them. The first one is line coverage, and with an example of Fibonacci function that calculates the nth element of Fibonacci sequence, we will see how it behaves. So when we call Fibonacci function and pass 0 as argument, with the line type of coverage, the whole line will be marked as covered. However, it's not true. Why? Because when we pass 0 as argument, only the left side of condition operator is executed and only the positive branch of ternary operator is executed. While the negative branch, where Fibonacci function is executed recursively, was not executed. So for developers, this is a bad type of coverage because it lies for us. It shows that all the branches were covered. Unlike line coverage, branch coverage understands what branches in our source code were executed or not. Of course, this is better than line coverage. And finally, condition coverage understands subconditions in condition operators. This is the best and most useful type of coverage, but unfortunately, by historical reasons, PHP unit by default uses line coverage, so the most weak one. However, it's good to know that starting from August of 2020, we can use path coverage in PHP unit and branch coverage as well. I really recommend reading this post of author of this pull request that describes in detail what the branch coverage, what the path coverage, and how it affects the time of PHP unit execution. Now we will discuss issues of code coverage, and I will show you why you shouldn't rely on it when it's used alone for the project, and why should not blindly trust it. So the first issue of code coverage is that it shows executed lines, but not tested one. Imagine you have a project and the code coverage equals to 100%. In reality, the tested code can be much less, for example, 60%. Why? Because of the reasons above, because line coverage shows line as executed, even if at least one of the opcode was touched on this line. The next issue of code coverage is implicit coverage, and let's have an example here. Imagine we have such a simple class, ID generator, that has only one method, UID, that generates unique identifier. Then we have another class that uses ID generator that also has only one method, create, and creates an instance of user. And before creating, it pre-generates using ID generator unique identifier. So pretty simple logic here. For this class, we write a unit test. Unit test is also simple. We create an instance of user creator, pass ID generator, call create method, and expect that the returned object is an instance of user class. When we run test here, the green will be built, and code coverage here equals 100%. And let's think here, did we really cover all the tests of our small application? Did we really write the test for all the classes in our application? No, because we covered only user creator class, but not the ID generator. So code coverage of 100% is a lie here, because we have an implicit coverage. What we can do here? We should use covers annotations. Covers annotation should be placed above the test class, and it says what particular source class is covered by this test. So when we put covers here and say up user creator, it means that when code coverage will collect its data, only user creator will be marked as covered by this test, but not ID generator. So we can use this annotation manually, or we can use it automatically by adding coverage listener from Symfony PHP unit bridge component. It will add it automatically for all the classes using PSR4 standard. When we run with this coverage annotation added above the class the test again, code coverage will decrease from 100% to 65, which is far better than it was before, because in reality, we didn't create a test for ID generator, and code coverage of 65% better represents the reality. So as developers, here we need to add additional tests that particularly cover ID generator class, which is cool, of course, because we will have more tests, more detailed tests for ID generator, and our test suite will be more reliable. Okay, as a conclusion here, code coverage marks as executed not only subject on the test, but all the related code that was executed together with the subject on the test. And to avoid this, please use covers annotation. I really like this image from Martin Fowler that explains what does well code coverage. It does well, it finds untested code well, but it doesn't find tested code. I will show you in a minute what it means. And at the same time, it doesn't say anything about quality of the tests. Let's look into this image. This is how HTML report looks like for PHP unit. When we see red lines, we can be sure that these lines were not tested because they were not executed. It's pretty logical, right? But we can say the opposite. For the green lines, we know that they were touched, they were executed, at least one of the opcode of each line was executed, but we cannot say that these lines were tested by our tests, right? So when you have code coverage of 80%, we can say that 20% of our code is not tested, but we can't say that 80% of our code is tested, because with line coverage, we have a lie here. And the last thing that I want to share with you about code coverage metric is a strategy that's named assertion-free testing. What does it mean? We can get any code that is covered by test. In this example, I got my own library that works with domain events. And in test suite, we remove all the assertion here, but leave the method calls. So we leave release events method calls, but remove these correct assertions. Instead, we replace them with this simple and dumb assertion assert true, which always pass, right? So when we run such test, they will always pass. Then the next step, we remove or change any business logic in our application that is covered by this test and run the tests again. After this change, we will have green build and the code coverage will be 100%. The tests pass because in each test case, we have assert true, which is always pass, right? And code coverage is 100% because we left all the method calls, so all the lines were executed. However, we dramatically changed the business logic of this method, and it wasn't detected by the test suite. That's why we cannot rely on code coverage alone, and we can't trust it. So how to measure the effectiveness of the test suite? How to measure the quality of the test suite? How to say that these tests are good enough and these tests are bad? What metric should we use for it? And here where mutation testing comes into play. So mutation testing is a methodology that step by step changes your code, integrates potential bugs, and after each small change, it runs the set of automatic tests and see if they fail. It means that the test good enough because they caught this change, because they detecting this potential bug. But if tests still pass after introducing a small change in the application, we can treat the test as weak because they didn't caught this potential bug. We will get familiar with the mutation testing algorithm more deeper in a minute, but first let's get familiar with basics of mutation testing. So mutation is a single change of code. When we change binary operator plus to binary operator minus, we call it a mutation. Mutant is a mutated source of code. This is a new version of our application. This is a result of mutation. So the code marked as green here is a mutant. This is a new version, right? And finally, mutation operator is a function that gets original code. In our particular example, this is a code in red. It takes as an argument original code, and by applying some mutation, it produces a mutant, a new version of the code. There are many mutation operators out there. For example, infection has something about 100.5 mutation operators. A couple of them represented here, such as changing return value from true to false, for example, modifying a regular expression in several ways, changing operator greater than to greater than or equal to, for example, removing arrays. Mutation testing libraries can change signature of our method, and we will see how it's done, and so on, so on, so on. So there are many of them. Now, what is how mutation testing algorithm looks like? So before we discuss it, I will answer to the most popular question that people who start using mutation testing asks. Do we need to write tests for our tests in order to check the quality, check the effectiveness of our test? And the answer is no, we do not. Mutation testing methodology uses existing source code of our application, existing tests, and by injecting the changes into the source code, analyzes how good the test suite is. So we will see how the one step of mutation testing algorithm looks like. Imagine we have a small application that implements calculator, okay? And on the line 30, we change the plus operator to minus. This is a first mutant. When this mutant is created, infection runs original test suite against this new version of application. So all the rest files are the same as original application. We just have one small change where on line 30, the plus operator is changed to minus. And against this new version of application, against this mutant, mutation testing automatically checks our test suite. And if tests fail, the mutant, the new version of application, the mutant is treated as killed. And this is a positive outcome of mutation testing. It means that our tests are good enough because they caught this potential bug, because the change in the business logic was detected in our tests. In mutation testing, we need to strive for failing tests. This is where failing tests are good things. But when mutation testing runs the test against mutant and they pass, the mutant is treated as survived, and this is a negative outcome of mutation testing because test didn't detect this change, this potential bug. That's why they are bad. Okay, after mutation testing, library injects all the potential bugs into your application and runs all the tests for each such case. It provides a result, which is called Mutation Score Indicator, or MSI. How is it calculated? This is a number of killed mutants divided by number of all the generated mutants, and for convenience multiplied by 100. How to understand it? Imagine we have a small application and a mutation testing library generated only 10 mutants for our application. And 7 of them were killed because tests were failing for them. In this case, we will have mutation score indicator of 70%. When we have code coverage of 100%, mutation score indicator with 70% is treated as a bad result. It means that 30% of potential bugs were not detected by our test suite, which is of course bad. We should always strive for mutation score indicator of 100%. Even if we have code coverage of, let's say, 20%, we should strive for mutation score indicator of 100%. It will mean that we covered only a part of our application, but we did it with a good quality, because our test will catch all the potential bugs in this covered by test part of the code. And one more important characteristic of mutation testing is idempotency. What does it mean? It means that for the same source of code, for the same test, we will always have the same number of generated mutants, and we will always have the same value of MSI. It means if you have a commit A in the master branch, you can run mutation testing for it locally on continuous integration server, on the laptop of your colleagues, and you will always have the same number of generated mutants and the same MSI. Idempotency here allows us to run mutation testing on continuous integration server. For example, if commit A has an MSI of 100%, and then someone adds commit B that added new, for example, files and new test, and mutation score indicator was decreased from 100% to, let's say, 90%, we can say that test quality has been decreased, and we can fail the build. We can prevent from merging this pull request to master because the quality of the test was decreased. And this metric, MSI, is exactly that metric that we were looking for to say that these tests are good, but that tests are bad. Okay, we can visually represent mutation testing as such grid. We have 4 mutations, right? And for each mutation, for example, for this one that changes the plus to minus, we run a set of automatic tests, let's say unit tests, each one by one, unless one is failed. When it fails, we mark the mutant as killed and stop here. We do the same for the rest of mutants. Someone can be escaped if no tests were failing. Someone are not. And after all the mutations, mutation testing library provides us MSI result. Now let's have a real example in PHP code. For this code, we will write a test, then run infection, and we will see with 100% of code coverage what is MSI and how we can improve the effectiveness of our test suite. How to understand this code? This is an object-oriented filter that gets an array of users, a collection of users, and filters out those users that are below some age threshold. Age threshold by default equals to 18 years and analyzed from constructor here. So those users that are above 18 years will stay in the collection and will be returned here. But those users which below this age threshold will be filtered out. For this code, we write a unit test. Unit test is simple. We create a collection with one user, which is 20 years old. We create an instance of user age filter. We call this filter and pass users collection and expect that only one element will be returned in a collection. And this is true because we have an original collection with one user, which is 20 years old. We filter it using this filter, this user is greater than 18 years old, right? And that's why it returns in the collection, and the number of items returned will equal to 1. So when we run this test, we will have green build and code coverage will be 100%. Now let's run infection against this small application again with those tests and see what the MSI is. When we run infection, we can see that 3 mutations were generated, only 1 mutant was killed, and there are 2 escaped mutants. With code coverage of 100%, we have only 33% of MSI, which is a really bad result. It means that 2/3 of potential bugs injected by mutation testing library by infection were not detected by our tests, our simple test. Our task here as a developer to understand what mutations have been generated and to improve the quality of our tests. So let's do it together. The first mutation looks like the following. I want to underline it that this process is done automatically by infection. We just step by step looking into it to better understand how it works under the hood. So the first mutation looks like the following. Infection removed the array filter function and replaced it with return collection. So we get a collection argument here and we immediately return it. No logic here anymore. For this mutation, infection automatically runs all the tests that cover this code. We have only 1 test, I remind you. And this test still pass, which is a bad result because such a dramatic change in our business logic of our source code was not detected. Our task as a developer to understand why it happens. Let's look into the test again and think what happened here. So we have a collection of 1 users. We pass it to collection. Here, this mutant just immediately returns it, right? And tests, of course, pass because here we expect that 1 element will be in the filtered collection. After some thinking, we realized that we need to update this test and add additional user so that original collection and filtered collection will be different in the size, right? After filtering out this collection, we will have only 1 user, which is 20 years old. And for this mutant, if we remove original collection without applying any filters, we will fail here. This assertion will fail the test because there will be 2 users with 15 and 20 years old, but we expect only 1 here. So we run infection again, and yeah, our MSI has been decreased from 33 to 66%, which is a good thing, but still not enough. Our goal, as I said, is 100% of MSI. Let's see how the second mutation looks like. Here, infection changed the operator greater than or equals to. It was replaced with operator greater than. And again, infection automatically executed the tests that cover this line, and they pass. Again, we do the following. We analyze our tests, updated tests, right, to understand why it happened. Let's do it together. So the first user was filtered out because its age is below than our threshold, which is 18 years old. Then we compare the second user. 20 we compare with 18 using the new operator greater than. And it doesn't matter with what operator we compare it with original code or with mutant, this expression will always evaluate to true, right? That's why test passes. So we need to update this test in such a way that will kill this mutant, that this test will fail. And again, after some thinking, we realized that we need to add such users whose has an age as the age threshold in our constructor, which is 18 years old. In this case, we change a bit expectation of our test here. We now expect that 2 users will be returned and only 1 user, which is 15 years old, will be filtered out. With this new test, we will kill this mutation. Why? Because now when we compare 18 with 18, using the greater than operator, it will evaluate to false. We will fail here. Instead of 2 items, only one item will be returned, and this test will fail. We run infection again, and yes, MSI is now 100%, and the code coverage is still 100%. So it took us 2 improvements to increase MSI, while code coverage was always 100%. That's why I said in the beginning of my talk that you should not rely on code coverage only. This is not enough metric to use alone for your projects, and you need MSI as well to know whether your test suite is effective or not. Okay, what else can mutation testing do for us? It can find useless code. Let's have a small example here. This is a method that finds and deactivates inactive users. So using Doctrine repository, we find inactive users in database, looping through them, call deactivate method for each of them, passing them to persist method of entity manager, and after the cycle, we call entity manager flush, which will result in many update SQL queries. So the logic is clear here. And when infection do its job, it says that, okay, I can remove this method, persist, and test will pass. And after analyzing what happens here, we come up with an idea that persisting already managed user entity that was returned by Doctrine's repository is not necessary, because this code on the line 8 does nothing. It doesn't add any value to our application. We don't need to persist entity that was in a managed status. So we can simply remove this code and our application will behave exactly the same as before. This code is not needed anymore, and infection helped us to find this out. I will show you the problems that mutation testing the methodology have, and also we will see how these problems are solved in nowadays. So the first one is speed. Imagine you have a test suite that takes 5 seconds to execute, and mutation testing library generated 10 mutants for your application. So in order to execute mutation testing process, we need n multiplied by t, which is 10 multiplied by 5, which is 50 seconds to complete mutation testing process. When your test takes 5 seconds, in the worst case, mutation testing can take 50 seconds, which is really a bad result. And in our real application, we have minutes of test suites, right? And the number of generated mutants can be thousands or even tens of thousands. And in this case, mutation testing would take hours or even days to be completed, and nobody would execute it nor locally or in continuous integration servers. Again, we have many solutions how to speed up mutation testing and how to increase the speed, but I will discuss it a little bit later. Now let's see the second problem of mutation testing, which is equivalent mutants. What does it mean? From math's point of view, b multiplied by -1 and b divided by -1 is exactly the same result. It's an equivalent in maths. And we cannot write a test that will pass for the red line and will fail for the green line. It's impossible. That's why the task of mutation testing libraries to avoid generating such mutants, because it will be wasting of time. We will not be able to kill such mutants because this code is equivalent. it does the same with slightly different syntax, right? And while this case is easy to detect and infection prevents generating this mutant, the next one, when we have two variables on the left and on the right side from multiply operator, is harder to detect. Here we should analyze what values can be in B and C variables. And unfortunately, infection and many other mutation testing libraries for other languages cannot prevent this equivalence. So sometimes mutation testing will produce equivalent mutants that we can and should ignore in our config files. Okay, how to speed up mutation testing? The first solution is to execute a subset of tests from mutated line. So remember our example where we had an implementation of calculator and changed plus to minus on line 30, right? So when we run tests for this mutant, we don't need to run tests from completely other files or completely other modules because they will never fail. We need to run only those tests that cover this particular line. And imagine you have 1,000 of tests and this mutated line covered only by 5 of them. Of course, it's faster to run only 5 tests instead of 1,000. This is what infection does under the hood. Next, we run the fastest test first. Why? Because this line that we changed plus to minus can be covered by, let's say, 3 types of tests. By unit test, which is very fast, by functional test that can take seconds, or by integration test that can take minutes, even minutes. So we run the fastest test first with the hope that they will fail first. And if they fail first, then the whole mutation testing process will take less time, right? That's why we reorder the tests that cover a particular line and start from the fastest first. The next solution how to speed up mutation testing is to run it in parallel. One note here that before using mutation testing in parallel, you should prepare your test suite to be executed in parallel, which is not always easy to do. Because imagine you have a test suite that works with database, read and write to it, right? When we split the whole test suite in 4 parts, for example, in 4 threads, then at the same time, 4 threads will read and write and delete from the same database, and they can break each other. Even if we use transactions can be timed out. They can lock. We can have deadlocks. So we still need to deal with it. And the right solution here is to use for each thread its own separate database. It can be easily done with such tool as Paratest that exposes a special environment variable for each thread of the test suite, so we can create a connection, separate connection to 4 databases. And the same goes for unit tests. They can read and write the same folder, for example, and reading, for example, already deleted in the neighbor thread file can also break tests. So before using parallelization in mutation testing, please prepare your test suite to be executed in parallel. Okay, next thing to speed up mutation testing is avoid useless mutation. What does it mean? We do not need to generate such mutation when we change plus to minus when arrays are allocated on the left and on the right side near plus operator. Why? Because we can add one array to another array in PHP, and this is a valid syntax, but we cannot have a subtraction of array because it's simply invalid syntax in PHP. This operation is not supported. So we need to teach mutation testing library to not generate some mutation, because it will be wasting of time and resources, because such mutation will be killed by the language itself, because this is an invalid syntax. And the most valuable and my favorite solution how to speed up mutation testing is to run mutation testing only for the changed files, not for the whole project, not for all the millions of files in your source code, but only for the changed files. How it works? Imagine you create a new feature, you in a separate feature branch, right? And you added only 5 files and modified 3 files. So in total, you have 8 files in your branch. So you can say infection to run mutation testing only for these 8 files by using these 2 options, git diff filter and git diff base. Git diff base is the base branch, which is master or main for our projects or any other branch. And git diff filter, this is an option that just proxies the same option for git, and A stands for edit, M stands for modified files. So using git, we create a diff between master branch and our current branch that we are working on. We filter out only added and modified files and run mutation testing only for these 8 files instead of millions files in our REST part of application. And of course, running mutation testing for only 8 files will take much less time than it would take for the whole application. So I recommend using mutation testing for changed files only if your project is big enough. The next idea to speed up mutation testing is the following. I said to you that one of the solutions to speed up mutation testing was to run the fastest test first, right? But this idea is the following. We can remember what test killed particular mutant on the first mutation testing run. For example, the first mutant was killed by the third test, the third mutant was killed by the second test, and so on. And on the second and subsequent runs, we can use this saved and remembered information and reorder our test in such a way that killing tests, this one, and this one, will be placed on the first place, like this. And other tests will not be executed because it's enough to fail just one test to mark the mutant as killed. So in the ideal situation, on the second and subsequent runs, we will kill all the previously killed mutants from the first shot. And it will save us a lot of time. We already implemented this feature in Infection, and here is an example how it improved the execution time for our test suite in my daily job. So on the left, we can see a mutant that was killed by 38 seconds, and it took to run 488 tests before this mutant was killed, right? So it took 38 seconds. We remembered that this mutant was killed by this test, and on the second run, we reordered and moved it to the first place. So next time when we executed Infection, it was killed by the first shot, and it took half of the second. And the whole process was taking 1 minute and 49 seconds on the first run, on the first Infection run, and it took only 38 seconds on the first run, which is a great performance boost. How can you use mutation testing on a daily basis? So when you write a feature and cover it by test or vice versa, you can run locally Infection using the trick that I showed you previously for only added and modified files. With an option show mutants, this will display all the escaped mutants to the std out, to your console, so you can expect them and do the same as we did in our example to analyze how we can change the test in order to kill such mutant, or what we should remove in our source code if this is a dead code or this is an useless code, and to improve MSI and strive for 100%. In this particular case, infection says us that it changed the public keyword to protected, but tests still pass. And what should we do as a developer? We have only two ways to go here. We should analyze the code, and if this method is really not public, we should set it to protected or to private, so this mutant will not be generated anymore, right? Or if this method is really public, we should add a new test that will call this method publicly. And next time when we will call infection, when we execute infection, and it will replace public with protected, this new test will fail because it calls this method publicly, but it will be protected. So this mutant on the next run will be killed. And you do it repetitively to kill all the mutants locally, and then you can push your effective tests for code review. Also, we can use infection on continuous integration server. There is an option that we can use to fail the build, which is mean covered MSI. We can say that as soon as MSI decreases below 100%, infection should fail the build. So in master, we have 100% of MSI, and when someone opens a pull request with 99% of MSI, we can say that the effectiveness and the quality of test suite has been decreased, and we can to disallow merge this pull request and ask developer to improve the test or remove useless or dead code to strive for 100% of MSI. Mutation testing can also help with code review. For example, if you are using GitHub, we have a logger that automatically adds comments on the diffs, on pull requests, and you can inspect that infection did such a mutation and tests were passing for this mutation, so you can ask your colleague to improve the test here by looking just on the pull request. Currently, infection supports PHP unit, PEST, Codeception, and PHP spec, so majority of developers are covered. And you can use Xdebug, PHP debugger, or Pikoff as a coverage driver. And starting from PHP 0.1, we can use infection with older version, and of course it supports PHP 8 as well. If you want to try infection for your projects, I recommend to install it using, for example, Composer or by downloading FAR distribution, or you can use our playground. On this playground, you can write some code, write some tests right in your browser, click run, and infection will be executed. It will produce all the mutations that generated with a diff, so you can expect what mutants were generated and what is the output of PHP unit. So you can play with it right in your browser. As a conclusion, using mutation testing gives us more reliable tests with less bugs, because all the bugs, potential bugs injected by mutation testing are now caught by our test suite if we strive for MSI of 100%. It can help us with code review. So if the build fails and you know that MSI should be 100, you can simply ask your colleague to improve the test before you can start reviewing the code. It finds dead and useless code, as I showed previously. And from line coverage, which is used by default in PHP unit, we go to condition coverage, because every single line, every single expression and sub-expression, sub-condition are now mutated and changed by mutation testing libraries such as infection. Here are some links. Please follow us on Twitter if you want to know more about mutation testing, some books about mutation testing, and my personal Twitter. Here That's it. I will be happy to answer to your question. Thank you.